Hello and welcome. I'm Bill Wake. We're here working on Parser Combinators. We're building a library of them, and we're basically done. I think there's a little bit of tweaking to do, but today's the wrap up. So I thought I'd focus on a code review and a little cleanup in some of the tests, and I think a little bit of changing some precedents just to make things a little more convenient. Okay, so let's see. I guess we'll go to the code first and then come back for a picture. Okay, so the core of this is Parser. And it gets a little confusing because there's generic types everywhere and all that. But basically, you have to understand a parse result says it's an enum, and so it's either a success or a failure. If it's success, we produce some sort of object. We don't specify the type here, and we also produce a slice of the input that is basically it's the rest of the input that we didn't consume to build this target. If it's a failure, we get an integer back that tells us how far did we get along our input stream, and what's the error message for that. Okay, so Parser uses that. It says there's an input type. I don't know what it is. There's an output type. I don't care what it is. And there's a core function. You're going to provide a parse function. If I give you a slice of some input, an array slice is a sub piece of an array, kind of it's an efficient way to do it. If you give me a bit of input, I will give you a parse result and tell you how it went. Okay, so I've got a picture for that. Let's go over here. Okay, so the parser is the thing in the blue, all right, in the box that says parser, and there's an input that comes in. Think of it as a stream of characters because that's probably the common case, but it could be tokens or numbers or whatever. We didn't specify the input type, but we do know that it's an array slice, so it looks like an array. And in our input, we got A, B, 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 C, D, E, okay, whatever all's coming in, and a parser. And our parser says, if you match A, B, 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 it's going to represent a crown, okay? And so in the results of this thing is on the bottom, it's either a failure or a success, okay? And if it's a success, well, we get the object that matched it. And if it's a success, we also get the rest of the tape. So in effect, it's a copy of the rest of the tape. And we match the ABBB, and we got the CDE left. So you hand back the rest of the tape, and somebody can call another parser on the rest of the tape and read the rest of the input. If it had failed, we'd get a message. Let's say we had A, CDE, no Bs. Okay, we'd get an integer that tells us how far did you get. So we got to slot 1 because we got past the A, which was 0, and an error message expected a B. Okay, so it would have given us that, and the whole the whole system we're doing is kind of encapsulated in that kind of result thing. It's a functional language approach, and you can see this notion of some types, meaning like the ors. So we had an enum of failure or success. So it's got to be one or the other. And if it's, we can also see the and types, the product types. You have an int and a string, or you have an object and an array slice of input. Okay. Now, I think I'll draw a picture for the rest. Probably should have done this before, but, let's say this is really the parser combinator insight. Okay, so we have a parser. I guess I can steal it from here. Okay, we can define a very simple parser. We call it satisfy. Okay, and satisfy says match one thing or don't. Okay, and you pass in a condition that decides whether it matched or not. Okay, so let's get a text there. Match one thing or don't. Okay, so if you match it, it's success. If you don't, it's a failure. All right. Now, when we look at this parser, like we don't know what's going on inside it. And the Combinator insight, that's my term for it. It's to say, like, our responsibility is to consume some input and produce a failure or success. Okay. This clearly does that. It'll consume one thing and move the slice forward by one, or it'll be a failure and say I failed at position 0. Okay. But we can also make other parsers. We can build them out of existing parsers. So let's say we had a satisfy looking for an A. I mean, this isn't our notation, but just to kind of convey it. Okay. And another one that looks for a B. All right. We can define new parsers that take old parsers as input and string them together. Okay. So I'm going to define a parser that is a many, we call it many one, meaning it's got to match one or more. Many one, and what's it takes a parser as input. So it takes a parser and it repeats it one or more times. Okay, and let me just shift the color because it's kind of a different level. Okay. How about red for a mini one? Okay. And this thing has to, when you set it up, it has to own a parser. Well, I'll say P for parser, but the P is really this. Where's my arrows? Okay. P here is really pointing to this parser, the satisfy B. Okay. And so the many parser says, you give me a parser, and if it works, well, what I'll do is I'll run it on your input and see if it matches. And if it does, I'll run it again and again as many times as I can. And then my output on success, I'll give you an array of these. It's 0 or more, well, one or more matches that match them. Okay, and that's a perfectly good parser for a string of one or more B's. Okay, and then we have another parser that's a sequence parser. So let's make that one. We called it and then, which is a good enough name. It takes 2 parsers as input. Okay, and let's paint it green. Okay, and here's the first one. It'll take this A parser. And then the second one is going to be our many parser. And what this and then parser does is it says, I'm going to try your first parser, satisfy A. If that works, I'm going to try your second parser, many one of satisfy B. If that works, then you've matched a single A and a series of one or more B's. I'm happy. That's what I expected you to do, and I'll return a success. Now, if you try and parse P1 to satisfy A and there's no A, then it fails. Or if you get past the A but there's no B's, then it fails, and it returns its failure condition at that point. But but in effect, what we've done is we've made this kind of composite parser. So this is let's see, this one is match A. Match A, and this one is match B. This one is match, well, we have a notation for this. We put in a star in brackets. That's a new operator that says match sorry, it's a plus for one or more, star 0 or more. So this is a prefix operator that says, take this parser and apply it one or more times. And then this one, it composes them. So it's match A. I don't know why I can't get these to default like that. Okay, match the A. And then we have a sequence operator, and then match the interior one, the second parser. Match B. Okay. And so this parser matches A and then B and one or more B's. Okay. And notice it's still conforming to this. We give it an input string and it returns, well, success, it returns some object and the rest of the input. This one returns a character A. It gives it an input string with A, B, C, D, whatever. It returns the A as an object, the string, and then C, D, E, B, C, D, E, the rest of the input. This one, if you give it B, C, D, E, it matches the B and returns the B and the rest of the input. This one, let's say it's B, B, C, D, E. This one matches both B's, creates an array of strings, and returns the rest of the input. And then this one takes the two and puts them together. Okay. And so this insight that says you have some very basic parsers, but you can build up all your other ones from as a composition of parsers. Okay. And combinator, I'm not sure how the word combinator, they're parsers that combine others. It's related to the idea of combinators in mathematics somewhat, I guess. It's certainly true that this was invented by people who were deep into functional programming and that sort of mathematical end of programming, I guess you'd say, or math. I'm not sure how you describe it, algebraic end or something. Okay. But this is what we're going to be looking for in the code, a simple parser satisfy, and then these more composite parsers that take parsers as inputs. All right, let me hit save on this before I forget that. Okay. So let's start with the simplest one, which is satisfy. And this is really the only leaf level parser we've got. Okay. Now there's a fair bit of boilerplate, and I really wish I could format this to reflect that. But because we're a parser, we have to define an input type and an output type. Okay. And we have to have a parse function that takes an input and produces a parse result. Okay. So this thing is going to have, it really takes two arguments. You have an optional message that we just default to did not find expected value. And you have a condition, which is a function from input to Boolean. So I look at one input and I give you kind of a success or failure Boolean, a function that can decide if it succeeded or not. And so the parse is take the input. If it's empty, produce the message. If the condition, that's our little function, succeeds on the first object, return success, and basically slice off the first item from the tape and return the rest of the tape. And if it returns, if it doesn't find what it's looking for, it returns a failure with the start index and the message. Okay. So this parser is just sort of the match one thing parser, the bare minimum kind of thing. Everything else, this is the only one that actually consumes input directly. Okay. You can write your own like this, and we will have to when we do real programs, but, it's kind of the bare minimum. It's the one that's actually chewing through the tape. Okay. The others all build up from that. So let's take many one. Okay. Again, it's a parser. It's got to have an input and an output defined and a parse function. Okay. The only thing it takes as input is setup. It needs to know the parser that it's going to be repeating. Okay. So you create a many one with some parser, and then it's a little more complicated here. Okay. What we're going to do is we're going to create an array of targets, because many1 always produces an array as an output. Okay. And we said target was array of p.target. So whatever our parser sends us back, we're going to build an array of them. Okay. So create an empty array, start at the input, and then parse the first one. Okay. If the first one fails, let's jump down here, then we failed, because this is many1. It requires at least one match, and you didn't have a match, so you fail. All right. If it succeeds, well, we're going to capture the value that it returned, and we're going to say, okay, now last remaining is where we pick up parsing. We're gonna go around again. Okay. So we've got the first one that's required, and now we're going to do a loop. Okay. So we're going to try and parse with the rest of the tape. And while we get a successful value, we'll keep appending values and then chopping off the part of the tape and parsing the rest. Okay. We'll keep parsing. And eventually, we know we're in a success case here because we had the first one match and we need 0 or more. We got an array of values and whatever tape was left. Okay. So that just works. Okay. Now I'm going to look, the mistake that would be easy to make, it would be easy to mess up the remaining piece. So we need to make sure this is moving forward, but last remaining is the rest of the input from the first one. And then here it's again the rest of the input from there. So we're definitely proceeding through the tape. Now finally, it's handy to have these, rather than calling, nested functions or nested objects of, an and then of a satisfy, comma, many1 of a satisfy. We can do these operators. Swift allows us to define our own operators. So we'll define plus. Usually, most grammar notations have a notion of repeating one or more times. So regular expressions use plus as a suffix, and there are grammar variants of context-free grammars, kind of one level up, that use plus. Some that use I'm not sure what they have braces for 0 or more. Maybe it's they probably just do repetition for the other, but that's okay. At any rate, if you put plus in front of a parser like plus satisfy, you're saying one or more copies of that. All right, and so I feel like in a way, if you understand satisfy and you understand this one, you're going to understand the rest of them. Okay. Probably the next most similar is many. All right. And many is just like many1, but it is fine with 0. Okay. So the boilerplate up here is kind of the same. It produces an array of stuff. It's got a parse, and it accumulates target parentheses, creates the array of output values. And then it does the last remaining thing. Notice it doesn't match the first one like many1 did. It just starts in with 0. Okay. And we go through and try and match our parser, the parser we were given as setup, and we try it. And if it works, then we append the value and try again. Okay. So we're moving forward through the tape, matching as many of these as we can. And at the end, there's no failure return here. If you didn't match any, if the first one failed, it's okay. It's an array of 0. Okay. And that's the result you got. You said it was okay to have 0, and you do. So there's no reason to fail. All right. And we return that list of values and wherever we are with the rest of the tape. So very, very similar. It's a little simpler even. Now, I probably could have defined, you definitely can define many in terms of many1 or vice versa, but we didn't. Okay. Should we? Okay. We probably could. See, the thing is, we probably developed this before we developed sequence and stuff like that. So let's say this is the fundamental one of the two. It's saying you must match 0 or more. Okay, we can write many one. If I wanted to say what many one is, it's really parser and, well, I guess I'll use our notation, this and that. Okay, so it says you must match 1, and then you match 0 or more. Okay, so I'm gonna tell you what. Let's look at sequence first, and then we'll try and redefine many one. So part of my reason to do a code review is to simplify where I can, and I think this is just the fact that it grew up in a different order. Okay, now this one is where things get repetitious, and I don't see a way to easily fix that, unfortunately. Okay, so we'll look at this, and then we got a bunch of variations is what it boils down to. In a way, this is the most primitive. It says I'm gonna make a tuple out of your sequence. So you give me A followed by a B, parser 1 followed by parser 2, and I'll make a tuple of the result of parser 1 and the result of parser 2. A tuple is kind of an anonymous pair, if you haven't run across that. All right. So P1 is of a parser type and P2 is of a parser type, but they don't have to be the same types. We enforce that they have the same inputs because we don't know how to parse it if it's not all the same inputs. But we don't care about their target types because our target is this tuple. So it's an anonymous pair, an anonymous type with the first target and the second target. Okay, so to set up, you've got to keep hold of those parsers. And then the actual parse method, we parse with the first parser, and I'll jump down to 38. If that fails, okay, well, then we return that failure, okay, because you're supposed to match A then B. If you don't match A, you failed. Okay, now if our first parser comes back with success, we got the target, which is the object or value it produced, and we got the rest of its input. Okay, so we'll take parser 2 and feed remaining 1 from here to here. So feed that into the second parser and get its result. Now, again, jump to the failure first, which maybe it's more readable this way if I put it first. It certainly seems easier to explain. Okay, let's do the same thing here. Okay. So if it gets past the first one and we run the second one, if that one fails, well, we failed. But we did get past the first item, so our failure message comes from the location here, not from the first location. So as we're parsing through, we can say, I got this far. So I got past the A and I'm looking for a B, but I don't see any B's, and I'll tell you the location where the B is missing. Okay, so we produce a failure if the second parser fails, but if the second parser succeeds, now they've both succeeded. We got a target and a remaining, and we're going to return a pair. Well, success says return a value, which is a tuple in our case, target 1, target 2, and the rest of the input. So we consumed the input for the first parser and the second parser. We've got the rest of the input is remaining 2. Okay, so that's our and then tuple version. Okay, now that will work fine. Okay, we don't have to care about compatible types or anything. It's just it returned 2 things. We're fine. But there is a case if the 2 types are equal. So they in this case we're going to say and then array. If both parsers have the exact same type, the same input type and the same output type, well, I'm producing a tuple of 2 of the same type. It would be nice if I would just give you an array back. Okay, so that's this notation. The new target is going to be an array of the original target. Okay, since they both have the same target. Now, this is the problem I have. This code is so similar, and I'm going to swap these around because I think I convinced myself it actually makes the most sense. Whoops. Only if I do it right. Let me, okay. All right, failure. And then down here, I'm going to do the same thing. Yeah. Okay. Now, this is what bugs me, right? This code is basically the same. Run the first parser, run the second parser, do this, do this. The only difference is down here, instead of returning a tuple, we return an array. Okay, let me rebuild. And the problem is these don't have, I don't think I can make these like inherit. I haven't tried it. Okay, I have not tried that. Let's see if that's true. I got a feeling it won't work, but let's try inheritance with and then. Okay. All right. But the body is basically the same except for this. So the question is, how do I compose the result? Yeah, I don't think that's why I don't think inheritance is going to work, because I could imagine writing a routine that give me target one, target two, and I'll return back the object that it should be. But I can't say it's going to be an array of stuff this time and a tuple of stuff that time and something else some other time. So I feel like I'm stuck. Now there's some Swift has a type called any that lets, it's kind of like a void star in C or C++ that lets you return any type back as the contents. But then I can't explain that my parse input type, my target type has changed too. Okay. And so I think, yeah, it's not going to be an option because I can't, there's no inheritance mechanism for this. All right. So let me take this out. All right. Now I'm not the expert on Swift or anything like that. So it may be that there is a way to do it. And I would really love for somebody to come and say, hey, it's easy. Why don't you try this? And it works. Okay. But I don't see it. Okay. I hate it that I don't see it, but I don't see it. Now, I think the only way I could see it working, and I believe we did try this, but you can't parser right now. Parser's a protocol and can't be made generic. It may be that the new version of Swift that's coming out definitely improves some of the stuff around protocols versus generics versus I don't know what you call these, but constrained types and stuff like that. It definitely is an evolving area of Swift, and it may be that the next release will let me put a generic type here that I could reference here, and then I could override here, and make it work. I would love that because I hate the duplication. All right, and the deal is I've got a bunch of these because I've got produce a tuple, produce an array. Well, if you have two elements the same, you can produce an array of them. But what if you have one element of a target type? Let's say P1 is an array of the type of P2. So I have something that's an array of stuff. Many satisfies that produce an array of strings, and I have a string coming back from this one. It would sure be nice to just append the string into the array, all right? And that's what this one does. It says there's an array then an element, so P1 target is an array of the same type as P2, so they're compatible. And then down here, where's our success? We've built an array of the target 1 is an array. We've appended target 2, and now we return that. Okay, so again, it's combining target 1 and target 2 into an array value. All right, and that works nicely for those situations where you as you're building things up. So I'll just put one in. If I said star of well, I'll say match A, okay, and match B, okay. Star binds tightly, so it matches 0 more A's, so it produces an array of A's, array of strings, and then this one produces a single string, and then array element says, oh, this should be A, B. Okay, assuming you had one input and so on. And if it had none, it would just be B, and that'd be the way of it. Okay, let's flip the successes and failures like we did before. On both branches. Okay. And the next one is the opposite. It says I matched an element and then I matched an array of the same type, and my target, the target of the array piece it's an array of P1's target, so it's compatible. Okay. And again, we're going to see build up something from target 2. We insert the thing at target 1 at the front. Okay. Is that right? This is element array. Okay, so the element gets inserted at the front, and then we return that array. All right, and again, I'm going to force my code to be more similar. Here. Okay. Let me just run all my tests. All right. Now, another variation. There's times where you're parsing two things. They have to both be there, so it's a sequence, but you don't care about the thing on the right. So, let's see. What would be an example? I don't know, the thing on the right. Well, it depends how you do it, but let's say you were matching expressions followed by commas. So think about an array definition where you say, like, A equals, and then you say 1, 3, 5. And in a lot of languages, you're allowed to end the list with a comma, sort of for a symmetry. If they're one per line, you can cut and paste the lines easier. Okay, so I've got the 1 and the comma, but I don't care about the comma. I need it there, but I don't want to keep it. And so this operator says, let's say if you just said match, well, let's say number, we'll assume it's a parser of some sort, number, and then we want to keep the number, so we're going to do a sequence, but we don't care about the comma. Okay, so the normal sequence operator has a greater on both sides, but when we leave off one side, we're saying just keep the side I'm pointing to. So only keep the number, okay, and throw away the comma. We need to match it. It has to be there, but we don't want to put it in our result type. Okay, so it's kind of all the same again, but the only difference is the return value. We just return target 1. We throw away target 2. That's the underscore there. Okay, ignore a variable that always ignores its result. Okay, so we only return target 1, all right? And then there's a keep right, which again is identical, except we throw away target 1 and return target 2. Okay, but let me swap the failure successes like I did the others. Okay, and this one. Okay, and this. Okay, so that should all pass its tests. Okay, so let me push this. So in the and then parsers make the failure case first in each switch easier to understand and explain. Okay, so yeah, I got 5, 6 different parsers that are basically the same. Ugh. Okay. And then we also define the operators. So this ampersand, this one says if you have the 2 parser types, and basically the type checker will say if they match, then we can return and then array. If they don't match, we can return and then tuple. If one's an array, one's an element, we can do that. If one's an element, one's an array. Okay. And then the keep left and the keep right. All right. And those, that's, I don't know, it's probably the biggest file because of all these variations that are so darn similar. But I don't know. We'll see what we can do. Okay. Let's go on. What's next? I think or else. Okay. So, and then says stuff has to happen in order. Or else says you can do this or this or this, and it's going to try things. Okay. So if this one doesn't work, I'm going to try that one. So it takes 2 parsers. They have the same input and the same input and the same target. I don't know why I put input last. That seems like you'd want to know it first. Okay, so P1 input equals to P2 input. P1's target equals P2 target. And our resulting target is going to be P1 target. Okay, we have parsers. Okay, so what we do is we run parser 1. If it succeeds, then we're good. Return it. Okay. If it fails, we're going to try parser 2 on the same input. We haven't, this is, I described somewhere along the way as saying these are backtracking parsers. This is kind of where you see it. It tried to do the input. It failed. However far it got, it could have gotten a long way. But we gave up, and then we try the next one from the same original input. So this is the backtracking part, the retry part. Okay. And if the case for the second one succeeds, then all is good. One or the other passed, and we're good. Return it. Okay. Either one's a success. The question is, what happens when both of them fail? And we have to return some sort of failure. Okay. And this is best failure is going to do that. Okay. So basically these things, I think a little formatting might help here. Okay. We're going to keep track of the 2 failures that we got back. Okay. So result 1 is a failure at this point, and so is result 2. Okay. So we're doing a guard to kind of convert them. We know well, interesting. we know it has to be a failure. Failure one has to be a failure. If it's not, we're just going to return failure two. This is almost a can't happen case. I don't know if that's. Yeah, I don't. I think it's kind of can't happen because you won't get down here unless it is a failure of some sort. Okay, but in any case, to satisfy the compiler, if nothing else, that it really is a failure, we've pulled out the two locations and matched it as being a failure. Okay, and then we're saying which is the best failure. Well, it's going to go by locations. So if the first parser got farther, let's return it as the failure. If the second parser got farther, then return that as the failure. Okay, so imagine it's going partway into, it thinks it's an expression and it finds a problem. And then the second parser thinks it's an array reference and it finds a problem. It's like we'd like to kind of take whichever one got further and say that's the one that really should report the message. So this little function basically does that. In reality, I could report 0, or the starting point of the input. Really, it doesn't have to be 0, but I could report the starting index, and that would be fine. This gives me a little more error messages. So if I only reported the starting index, right, everything is going to boil down to starting at the first character. I can't parse the thing, so the error is going to show up at position 0. Well, that's not what we want. We'd like to see, what did you really think it was? Okay, but yeah, that's the reason we're doing this stuff. The original version just returned a failure with start index, I think. Okay, and then we also define an operator. It's or. It's very much like an or. So we got it wrapped in less than greater. Okay. Let's see. Let me compare this. I guess I can do that on check-in. Okay, I swapped the order, formatted that. Okay, let me just run tests. Okay. Alrighty. Moving on. Okay, what's going to be an interesting one from here? Well, I think the next one to look at let's do optional. Okay. So optional says 0 or 1, and in Swift you can say something is optional by putting a question mark on it. So it's going to return, if your input was a string, it's going to return a optional string. Okay. Well, I guess it's really what your target was on your parser. But so what happens is we try and match it. If we succeed, we return a success. If we fail, we still return a success, but we return the nil, saying you had 0 of them, but that's acceptable to me. And notice here we return the whole input. So you matched 0 characters, and that was fine. So don't move through the input. All right, and it has an operator, question mark. It's a prefix operator. All right, very straightforward. Let's see. How about let's do name. That's a little interesting. The problem is, and I don't know. This is kind of a compromise thing. Let's look at the tests on that. I think it'll help. Okay. So we have a parser satisfy that looks for a 1 and another one that looks for a 2. If you run this without this, so let's comment that out and run this test. Okay, we're going to get a different message. The message we, oh, name is not used if parser succeeds. I'm sorry, that's not the right test case. Name is used if parser completely fails. Okay, so here we got sat1 followed by sat2, or sat2 followed by sat2. Okay, and it should be either 1-2 or 2-2. If we fail to match, so we're parsing a 0, which is not going to be a 1-2 or a 2-2, we get an error message. Let's run this. We expect this line to fail. All right. Our messages did not find expected value. Well, I'm sorry, that's not very helpful. Okay. If it were only looking for exactly one value, that's fine, but it's not enough. Okay. And so this percent thing lets you attach a name to a grammar. Okay. And so when you attach that, then the message turns into should be 1-2 or 2-2. So it's at the precedence of the or operator, and it's sort of like saying if this alternative failed and this alternative failed and this one failed, what should you report? Okay, well, you should report this message. All right. And so rather than the more generic message that might come from these rules, because A or B or C or D, the only thing common is it's not something I expected. This lets you be explicit. And so it's, so even if it gets partly through, it found 1, but not 1, 2, we can get the more specific message. That's fine, even though we have this one available if it completely fails. Okay, so the partial failures, we can take the messages from inside. That's the most specific thing. But the general failure of a bunch of alternatives, it's nice to have a separate message. It's a little bit of a kludge, but it's not an impossible kludge, I guess. All right, so let's see how this thing works. Okay, so what it does, it's going to parse parse the expression, parse the input. If it succeeds, then we're happy. We don't have to worry about messages at all. Okay, but if we see a failure and the location is beyond the start index, so it didn't fail the whole alternatives, it got partway through one, let's take that. Okay, so we'll use the location if we have one, but if we don't have one, then use the name, the message here. Okay, so this is sort of a worst case failure. At least use the new message here. Maybe this is overall message. Default message. Yeah. And I'll take this one too. Okay, I think that explains it a little better. This is the specific message. This is the default message, and maybe that would be good too. Okay, so if the location is into the thing, use the specific message. Otherwise, if you're back at start index, use that. Okay. All right. Let's do one more of these kind of parser-oriented ones. All right. This one is the comma operator, And there's two versions. I guess maybe we'll look at the operator. We're used to these things now. So it's kind of like exponentiation, and so I think the precedence is wrong. That's where I wanted to deal with that. So this is comma operator precedence. Okay, we'll deal with that later. All right, but this notice instead of 1 ampersand, it's got 2 ampersands, kind of saying repetition. And so the deal with this one is, imagine, well, let's say you're making a function call, f of a, b, c. Okay. One way to describe this is variable and 0 or more copies of comma followed by, well, we've got to keep right, so we can do this. We can ignore the comma, but keep the variable. Okay, maybe it's a formal function parameter definition or something. Okay, so you match the first variable and 0 or more comma variables at this point. Okay, well, that's kind of repetitious. What we're going to do instead is use this operator. Okay, if I say variable and match of comma, sorry, it's and less than is the new way to do it. Okay, this says take this variable and intersperse commas, or kind of separated by, maybe is the way to read this. Variable separated by commas. Okay, and we could have this form if we wanted to keep the commas, but in this case the comma doesn't give us any information. Knowing it's there is good, but it doesn't really help us anything. It doesn't go in our tree, put it that way. So variable separated by commas. Okay, and that gives us this nice concise form. We don't have to spell out all these and remember that we got to do this and forget this and all that. So it's a handy little thing. Now, as I say this, comma maybe isn't the best name because it doesn't have to be a comma. I said separated by, and I think that's the right name for this thing. Okay, so P1 separated by P2s. Okay, and if it's commas, it's P1 separated by commas. Good. Okay. All right. And do I have the name? Well, I don't really have that name, do I? Okay. And then comma left. I guess separated by left is going to be good enough. By left. Separated by keep left. Okay. Good. All right, let's make sure test path. Okay. That's a good one. All right. Now, what else have we not covered? Okay, and then we haven't done bind, check, peek, and pipe. Okay, let's do bind. And again, I'm going to go to the test to explain this. Okay. The deal is some grammars are recursive. Okay, so let's see this one. We got digit that satisfies matches a 1, and we create a number parser that binds digit.parse. Okay, let's do this one instead. Sorry. This one's more recursive. A 1 matches this, and we've said let's produce an array of that. Okay, so normally we just produce the integer itself. We want to create an integer array. All right, and then 2 matches a 2. So we're saying let's bind to create this recursively. I want to talk about expression. So I want to say expression is equal to some function of expression, but I don't have the name, okay, because you can't put it on the left side or put it on the right side until you got it on the left side somewhere. So what I do is I define expr as a bind type, and I'm saying it's going to be there, I promise. It reads integers and it produces an array of integers, okay? And now I can reference that parser. I can say I can look for a 1 or a 2 followed by an expression. So if you think about the way this goes, I could match 2 expression could be 2 expression, and then match a 1. Okay, so 2, 2, 1. And I'm imagining this kind of analogously to like a minus sign. So think of 2 as representing a minus and 1 as representing some number. And I could use recursion to define this loop. Okay, so 2, 2, 2, 1 gets matched because it can match 2 followed by expr, which is 2 followed by expr, which is a 1. Okay, and so it's a 3-step dance. You define the name of the type that you want to make recursive, and then you create a parser that uses it, and then you bind the parse function into this object. Okay, notice it has no parser when you create it, so like there's no argument going in which is a parser, right, or anything like that. So we have to somehow tie it back together, and we do that by giving it a parse function, and in this case parser. Okay, and so it gives us what we were after. So the 2s, notice they returning just their own value, whatever value they had. Okay, so the 1 produces an array of integers. Expr produces an array of integers. So the 2 sides of the OR bar are the same type, which is what we require. All right, and how does bind work? Well, it's not too bad. The fact that you need it and how you make it work, I mean, I definitely took that idea from somebody else. Okay, but what we've done is we said there's a parser function that looks exactly like our parse input function. Array slice goes to parse result. Okay, and then we create one that we hold, and by default, it's empty. Okay, now we have a variation of this that you can pass the function directly if it's not for recursive cases, but maybe you had a function that was named, parse number and instead of parse, and you want to convert it. Okay, but in the normal case, this is empty. Eventually you call bind and you assign the parser function. And then when you use it, you first make sure it's there and then apply it if you want to parse. Okay. So it lets you, it has a couple side effects. It simplifies the type because the bind you define the input and output type directly. So instead of keeping track that this is an or of an and of a multiply of a this of that, it's in there directly. Okay. And well, we got a few more, but it's been an hour. So let's take a break. We'll come back and look at pipe and check. They're the 2 functions that deal with the functional programming aspect a bit. So 3-minute break, and we'll come back and wrap up on the last few parser types. Welcome back. All right, so let's look at pipe. The idea with pipe is we need to be able to change the types of results that we get back. Okay, and so this is written the hard way, but let's look at it anyway. So we're parsing a bunch of integers. We would like our result type to be a string, okay? But our parse directly, the satisfy just returns whatever it gets. Okay, so satisfy of an int. We're saying here just take any integer, it's fine. Okay, but the pipe, we're saying make a pipe of the integer to satisfy, and what type do you want to be? Sorry, clock. Okay, so the input is a satisfy parser of integers. It produces a character. How does it produce it? Well, it accesses the letter corresponding to the index. So it really only works for 0 to 4. Okay, but if you parse 1, this pipe is going to match the 1 from the satisfy and then run it through this function. Okay, so this is a closure, it's a function, and position 1 is B, and return that value. Okay, now, yeah, here's the pipe operator. That's probably the way to really look at it. I don't think that test is really helping anything, actually. We wrote the test before the operator existed. Okay, let's look at it this way. So satisfy int matches any integer, and then pipe it to a function that turns an integer, $0, into a string value, okay, or a character value. And again, it's the same body. Let's change this one. I think we've got a number of tests that rely on that don't use the operators. So make tests use operators where reasonable. Okay. All right. So this one, we can definitely write it the same way. Is it the exact same thing? Sat one array? I believe it is. The difference is our sat is failing every time. It just says I always fail. Okay, pipe 1, satisfy int, character, sat 1. Yeah, I think that should be the same. Okay. So this one, if you run the parser, well, this one it succeeded, but if the parser fails, well, we just get the message that parser delivered us, the message. Okay, it doesn't try and do this function. So the function only applies if it succeeds. All right, and let's make sure the tests work. Okay. Okay, so we actually saw this somewhere where we converted the result type to array of integers. Okay, but so this is handy for shifting domains, and you know, if you map things, like the goal of parsing is not just to match a string. Usually you want to produce a parse tree, and we went through the example with the grammar examples yesterday. Producing expressions or statement trees, and since you want to produce a tree, the tree is a different type than the input. Like our input is probably characters in most programming languages, characters, possibly tokens if it's the part of a compiler, but we don't want to produce tree. We want trees. We don't want tokens or characters. So we have this function lets us turn them into trees as we go. All right, and then there's another one that's somewhat similar. This is check, and what check is going to do is sort of like match a precondition. Hey, shebang, nice to see you. So the precondition. So think about. Let's see. What's an example? The thing is, there are languages where you need some look ahead to get anything done. All right. The one I know was happening at one point was C had this problem. Well, maybe I can do it in BASIC. BASIC, you were allowed to have unary minus. Okay, so I can have minus b squared, and you also can have a minus sign, and you could have a minus even. Okay. Um, this minus, it would be handy to know, like, is this minus preceded by a value of some sort, like this, or is it a unary minus? And so you might want to go down one path for unary minus or another for regular minus. Another situation would be, well, I was thinking of something about in basic arrays access like this, and also you have user-defined functions that access like this. But, well, what I want to do is I want to see, okay, yeah, how about this? I want to know if this is followed by an equal sign. Okay. And if it's not followed by an equal sign, I don't want to treat it as an equation or something. So what check does is it says, I'm going to make a match, but I'm not gonna keep the results. If I fail to match, then you're not the right situation. So let's get the test. This is check. Okay. So I'm defining a function, a little helper. It says it's even. Okay. So it just adds up the sum of values and then tells me if it's a multiple of 2. All right. So this one is, we're saying I'm going to have a series of ones, and then I want you to make sure that it's an even number of ones. So I don't have an operator that repeats exactly a multiple of 2 times, right? We don't have a parser like that or a combinator like that. And so we're using some semantic functions to enforce it. So it's saying produce a string of 1s followed by a check that the sum is even, and only keep the left-hand side. So we don't keep the function, we're just keeping the parsed value here. And so if we give it 1, 1, 1, 1, then it's got 4 1s in a row, that's even, sum is even, and it's fine. Okay. Now if it fails, here we have 3 in a row. Okay. It's going to return a failure message. In this case, the message's sum was odd, and it tells how many it had or how far it got. Okay. Where's the failure? I guess the thing does it. Okay. And if the first parser just failed, like there weren't any 1s, this never even gets called. Okay. So another place you could think of this being, think of type checking, right? I could have this be some sort of complicated expression, and then this thing could come in and say, hey, you didn't try and add a string to an integer, did you? Because I'm basic and I don't allow that. Okay. So, it doesn't change the parse, but it can make it fail. So it's applying, non-grammatical rules to a parse. Maybe that's a way to say it. So normally you have regular expressions match one level of a language, context-free grammars match a second level, then the next level is context sensitive, but the parsing algorithms are so complicated, we tend not to use it. We tend to just use functions that can check the context. That's what that does. Okay, let's look at it. All right, and I think it's what you're going to expect. There's a parser, there's a function. Notice it can produce int string, which is our error information. All right, and so you've got the function, you call it. If it fails, well, you return that failure because the parser failed. If it succeeded, then you call the check, passing in whatever the parser produced. And if the check fails, so it's not null, it's a location and message, then you return a failure with the message from the checker. So your type check failed, okay. And If the check message didn't fail, then the original parse was fine and we just return it. All right. So, I mean, Swift's a little verbose on it, but it does what you expect. And then there's an operator definition that just calls that check function. Okay. Let's. Oh, I don't want to keep that. Okay, nothing major there. All right. Let's see what we have left. Okay, bind, check, mini. Peak is, I think, the only one left. All right, so peak. That's the one that's doing a preview. Okay, so what peak is going to do, again, I think a test is probably the right place to look. Okay, so peak is going to look at something and see if it sees it, and if it does see it, it's fine. It just returns nil because we're just peeking. We don't have a value we're forming. We're just making sure something is there. So in this case, we're looking for a 1. We're going to parse and make sure the 1 is there. And actually, I just return a 0. And returns a 0. Okay, yeah, so it doesn't return any information at any rate. Okay. Normally we would ignore it. And normally the usage is more like peek and do some processing. So I might want to verify. I just want to kind of make sure I'm going down the right path, basically. If the thing doesn't find what it's looking for, it does fail. So it gives the failure index and the message. Okay, so a peek that doesn't find it is a failure. And I don't know, does our README explain this better? Run the parser if it fails, if it executes returns. Yeah, it lets you fail early rather than go down a long incorrect path. You know, it doesn't really add anything because, well, yeah, it doesn't really add anything because you could go down the path, but we use backtracking, so we don't want to go backtracking forever. And this might let you do an early check for something. I don't know if it's super useful. It's, you know, we may go through and never use it. I don't know. We'll see. Okay. But I believe we've been through every file here. Okay. On the, at least the production side. All right. Let's take this. Okay. Now this, let's deal with the test first. I don't know. I don't think it'll be that hard. All right. So what I'm looking for is places where we've defined an operator, but we're not using it in our test. And the reason they got written this way was because they were written before the operator existed. All right. This one, and an array, satisfy int, sat1, sat2. It's really the same as sat1 and sat2. Okay. And that's just the more concise way to say it. Same for this one. And the array sat1, sat2. Okay. Okay. It's very common that we have 3 tests for these things. Okay. And then operator sat1, sat2. Well, that looks like that test got added once the operator got there. So this is redundant. All right. Let's run these tests. Okay. This one uses it. This one does. I imagine the rest do. Once the operator was in, it was certainly easier to keep using it. Okay, good. Bind tests. That's okay. Yeah. This one, you have to run it manually, so that's annoying, but again, I don't have a way around it. It's like it's supposed to throw you in a debugger, and if it does, it does. Okay. Comma tests. Oh, I should rename this to separated by tests. Get the comma word out. Okay, but that's this operator separated by. And we are using the operator, so that's good. Separated by keep left, matching one item. Okay. Error reporting tests. Okay. I don't think. Yeah, these don't really use. They're using the operators. There's a little repetition in these tests about the matching. I don't know if there's a way around that. We have a check failure. Let's see if that thing can do the job. Check failure. Give it a parse result target. Where target is equatable. That's probably the issue. Sorry, this was error reporting. The target. Well, let's see if we can put it in and what'll happen. I do feel like it's not. We want to do result dot check failure. Parse result 0 did not find expected value. Well, that seems okay. No. Input tires, generic input cannot be inferred. Okay. Let's find a usage of this. Oh, dot failure. I always forget to put that on. Dot failure. Okay, that can be used here. Zero did not find expected value. All right. Always nice when something gets a little simpler. Okay, we just did these tests a couple days ago, so I'm not gonna go too far. And I think we had to do this. There's something about the matching that made it necessary. But let's try it anyway. Check success equals self, expected target, expected remaining. I think that helps a little anyway. Okay. So I should be able to say check success result. Oops. Result.check success. Expected to target and expected remaining. Okay, let's move this up. I don't know why I didn't think of that the other day then, if that's going to work. Okay. Didn't start at the top either, did I? Okay, test dangling else. Target equal. And this is going to be statement. You know, we did some work to make these work with equatables, and maybe we just didn't have that in place. I don't know. Check success. It annoys me to be cleaning this up now. It should have been done earlier. Okay, but again, this is statement.line. Make sure that's right. We used it down there. Okay. All right. That's grammar. Those are using the operator. Using the operator. Name tests. Yep. This one is not. I think this is duplicate 245 goes to 245. And the reason I only am testing the operators is I don't think I can't see a situation where you would want to avoid them. So, yeah, we're just going to test them. And, nobody wants to write that horrible expression that explains the operator without using the actual operator. Okay, this is peak. That's fine. We're almost there. Yep. And that's only satisfies bare minimum and separated by. Okay. Right. All right. So is there anything left? No. Okay. All right. Make test use operators where reasonable. Yes. All right. Comma operator precedence. I guess this is separated by operator precedence. Alrighty. So separated by tests. We may not have a test that does it here, but I think our grammar probably does. Yeah. Let's go to grammar. Okay. Yeah. Here, this parser, I have to put these parentheses here because the precedence of this is the same as the precedence of that. But I would really like to make this higher because I think of this as more like, well, I think of the ands as being like a multiplication kind of operator and the ors as being an addition kind of operator. If I do that, this one I think of as more of an exponent operator because this is basically repeated sequences. So it's a very concise form of repeating it, just like exponents are repeated multiplications. So I would like this to be the way I write that. Even I might add parentheses sometimes for clarity, but I don't want to have to in this case. I think it should just work. And I believe this is going to fail. Our tests will fail from this. Maybe even not build. So what do I know? Oh, there we go. Yeah. Okay. What was the failure? Well, let's see. If statement with a block of a print and a skip is... It misparsed. This one has two. We expected both to be parsed in the same, but it got repeated at a different level. So, yeah. So, okay. So to make this pass, Separated by tests. Well, I don't know if I can. Can I navigate in here? No. Okay, I can type it. Separated by. Okay. Multiplication precedence. I don't know my precedence enough in Swift. Let's say multiplication precedence. What are the precedence levels? That's the kind of question I like to see answered. Bit shift precedence higher than multiplication. I want left associative. Maybe it is bit shift precedence. I don't know. Bit shift precedence. Addition is higher than range formation. Couldn't you put these in order? We just want to know. Litigation precedence. No. This seems like such a basic question. Bitwise shift precedence is not associative. Maybe it doesn't exist. I don't know. I think I could define my own. Maybe that's okay if it's not associative. I mean, I don't think it makes a lot of sense. Would you ever have separated by this, separated by that? I don't think so. Let's try the bitwise shift precedence. I think that's okay. It's too bad there's no exponent operator because they would give it a precedence that we like. Infix operator precedence group. Precedence group. Oh, maybe I can do that. Precedence group name higher than. Let's try that. Okay, precedence group name. It's going to be higher than multiplication precedence. I'm not going to say lower than. Associativity is left. I'm not going to say assignment. Don't implement const can be everywhere. Well, I think the way we're using stuff, a lot of it is kind of const. These enums basically give you value types. Yeah, I don't know. I mean, I feel in Swift like it's not 100%. It's definitely not 100%. Pure value types or anything like that. But yeah, there's not a lot of times we're changing the arguments or anything like that either. I have to say. Okay, so I think I can just say exponentiation precedence here. Yeah, I mean it's definitely a reminder. Yeah, I mean all the stuff that we're doing with these functions and all that, it really is it's really not modifying any inputs or anything like that. And if I did, it would complain. Let's see, the one case I can think of, which one was it? It was, and then, one of the and thens. We had to create result types. Yeah, so this one was the case of an array plus an element equals an array. And I couldn't just use target one. I had to create a new array to copy it, basically, and then append to it. But yeah. Yeah, I mean, I would say when I was doing C++, I liked having the const there a lot, but in this, most of the time it keeps track of things enough that it knows. And it definitely has a different attitude towards arrays, that if you basically this, they do a kind of copy on write thing. So when I assign this array, it's not copying anything except maybe a pointer to it. But then when I append it, it says, "Oh, you didn't want to make you wanted a modifiable copy. Oh, okay. I'll just copy that now, and then I'll append target 2, and target 1 will be unaffected." So everywhere when you reference, even like passing an array into a function, it's treated as copied, but underneath the covers, it optimizes it, and if you don't change it, it doesn't worry about it. But I mean, Swift is pretty heavyweight I mean, it's not as big of a language as C++, I don't think. I mean, it doesn't feel as big to me, but it's probably 3/4 there, and it's got stuff that C++ doesn't, that it's dealing with, and vice versa. But because you can't pass an array by reference, it always is passed by copy. That's kind of the big place. It's easy to get confused on these things and end up changing stuff that you didn't expect to. But it does distinguish value types and reference types. So if you use struct, it's a value type. If you use object or class, it's a reference type. And classes can be modified and structs can't, and stuff like that. But it's a little confusing in that sense. Well, I don't know. I haven't found a barrier, put it that way. But I can understand the feeling like, oh, how do I know if it's changing or not? But most of the time, Swift pushes you towards value types and functions that don't change things so much that most of the time it's just not an issue. I guess that's my short explanation. I'm not super. I mean, I've been using Swift for a couple of years and a little bit more than that off and on, but I don't think I'm a super language expert, but that's kind of my feeling of it. All right, let me go back to this. What I've tried to do is make up a new precedence. Let's put it up here. Okay, and I'm going to use it here. Okay, so I'm saying I've got this new precedence. It's higher than multiplication, and it's left associative, and the ampersand separated by operator is analogous to exponentiation and uses that precedence. And my test should pass, and if it doesn't, I'm not sure what's going on. Yeah. All right. So what we did was we made separated by have a new exponentiation level precedence higher than multiplication. Okay. All right, and that is that one. Okay, so let's push this. We got two separate projects kicking around. That's why that's going like that. All right, but this one, we're caught up, right? Okay. If I look in here, basically, I want to tag this. And I'm not sure I remember how to do it, but I think we're ready to call this version 0.1. Woohoo. Well, let's tag it as 0.03 first. So 0.3. Let's see. I guess new operators with a new precedence for the separated by parser combinator. Cool. Yeah. Okay. So this, I should be able to update this now to pcombo 3 update package. We changed some things, so there may be some changes in tests or whatever. I think mostly we added, though. I don't think this test is very deep. Not at all. Okay. But on the other hand, I don't think it updated. Oh, I got to push. Where is that? Push, include tags. All right. Yeah, that picked up. Good. Okay. So I think, let's see. I think we want to tag this as 0.1.0. And then release it. Okay, so is there anything else I need to say here? Well, I guess I'll let people take what they will from it. Okay, so we've tagged this. Let's do a push. Include tags. Okay, and let's update this again. Make sure that writes. Oh. Can I undo that? No. Can I? Okay. Well, I think we're to the more or less the end. The last thing to do is publish it open source, and I'll just pretend we've done it, and then we'll go do it. Okay. So up till now, whoops. Did I not save? Why aren't you registering? Is it F5? What's the update one? What's going on? So weird. Okay, let's go over here. Okay, so this one branch, 2 tags. Yeah, it's really 4 tags. Okay, let's go back. Reload this. Okay, 48 commits, last one 6 minutes ago. Good. All right. Right now, this is a private project. I think it's in settings. Down here somewhere. Change visibility. I think that's what I want to do. Is there anything else I've got to... I don't really care about issues. Make this public to anyone. Code is visible. Anybody can fork it. Changes published as activity. Okay, that sounds reasonable to me. Change repository visibility. Okay, let's go back to it. Well, I can see it here. It's public. All right. Woohoo. Yeah, so I think we are done with it. All right, now done is a relative term because my goal is to use this next week. I wrote a basic interpreter using recursive descent, and I want to switch over to using this parser combinator library and kind of explore how do you evolve from one, basically kind of an architectural evolution from one kind of parser to another. Lots of times you take big changes like this, and we'll look at a way to do it. I think, well, this is available on GitHub, so I'll send a tweet about that. I guess I can do that right now, right? Let's see, tweet it. In Swift as part of my recent Twitch. We just published it as open source. to say? It's been an exercise in developing a parser, but I plan to start using it in a real project next week. I'd love any feedback. And let's see if we can put this up here. Okay, we'll make that official. Alrighty. Okay, well, I think this is probably a good place to stop for the day. Good place to stop the project. It's out there on GitHub. Feel free to look at it and see what you see. Especially if you've got an idea for how to fix that and then stuff being so repetitive, I would love to clean that part of it up. I think the rest is mostly, it's not bad. There's not a lot of other repetition, but there's some opportunities. So thanks so much for joining me, especially the Onigum 069 and Shebang 0 has been around this week especially. And nice having your feedback and input, and take care. There's no session tomorrow. I'll be working next week. I'm going to try and do this experiment of integrating the parser and probably find out what's really good or bad about it. So there you go. All right, take care. Bye-bye.